into the meeting, I'd actually like to call on our good friend, Mr. Eric Heidendahl. Mr. Eric Heidendahl is one of those college to come up here and say a few words about his program, and evidently he imported some kind of contraband in his vehicle tonight. I don't know. Tell us about it, Eric.
Yeah, tonight, well, we've been encouraging students for a long time to make the meetings. And I'm happy to say that tonight we arranged for a van. We actually have 3 students here. So if you guys want to stand up, Ben Zupansky. And Syed Abbas. And Brian. And they're all third-year students and they're about to graduate, and of interest as well. Syed, put your hand up, Syed. He's our McCurdy Award winner this year, so as honored at the CCBE this year.
Nice. Welcome all 3. Thanks for coming.
Just to note too that Syed is originally from Karachi, Pakistan, and so one of the stories that he told me early on was that he said that he had departed Karachi and it was plus 40, and he arrived in Edmonton and it was minus 40. So it was a bit of a rude introduction to Canada, but he stayed anyway.
Yeah, we call that the Canadian 80 degrees of separation. So welcome everyone. So now for the second half of our evening, I'd like to actually call on my co-organizer Lee Whitcomb, totally against his lack of preparation, but I'm just going to ask you to introduce Randy, and then our next presenter, and then our third presenter, who can't introduce himself for obvious reasons. Lee.
Okay. So also, did anyone from the audience bring any gadgets? No? Okay. So I guess our first gadget is from Randy, who's everyone knows Randy, the Canadian governor, Fort Seven mentioned.
Okay, gadgets. What I thought I'd bring, it's interesting. What's the hardest thing to do in video? Does anybody know? Like the hardest process, the one that's the most intensive, requires the most, let's say, man-years of effort to develop? Frame rate conversion. I thought it was lip sync. Thanks, Dan. So, when you consider a video at 1 frame rate, I mean, it's a series of moving pictures, right? To another frame rate, the really easy way to do it is just to drop or repeat frames. That's pretty easy. Just insert the ones that where you need them, or take some out. However, when there's motion, if there's no motion, it looks fine. But as soon as you have motion, what happens is a smooth motion will start to judder. That's the term that's used to describe it. So you can start to apply more intensive processing than just dropping or repeating frames. So there's a frame rate technology called linear frame rate conversion. Now linear, what it tends to do is it looks at frames, and it really doesn't go much beyond looking at frames and interpolating what it needs to do to reduce the judder effect that you see. So what it tends to do is it will reduce judder, but it starts to introduce something called motion blur. The process that's used to go beyond that and reduce the judder and to reduce the motion blur is something called motion estimation, motion compensation. And it's interesting because when you look at this very, very difficult process, you can do it in a non-real-time based and do a very good job, but when you're in a live situation like the Olympics and a World Cup, there's still these specialized pieces of hardware that are used to do these frame rate conversions. So when you do motion estimation and motion compensation, you now move away from the frame or the field-based way of doing things and start to go right down into the pixels. So if you think of a soccer ball arcing through the air, you're actually looking at that motion, estimating where the ball should be, and then compensating those pixels and trying to recreate say, motion. So as a product manager over the years, it's been a technology that we haven't developed here in Toronto as part of the R&D group that I work with. And I've had the opportunity to pretty much talk to everybody on earth that has developed this technology and look at a way to bring the technology into the products. About a year ago, actually it's 2 years ago, a company came on the radar called Calibre UK. It's a smaller company. They work in the audio-visual side of things, and they work in medical imaging. So two related industries, not related to television as it were. And they had developed for large screens and for the medical imaging some very, very high-end, high-quality video processing. Developed a 2RU form factor, so that's what's holding up this monitor here. It's the monitor stand right now. But I'm going to turn sideways because that's how it would fit. It's essentially, it's a 2RU product. Its interfaces are all SDI, because SDI hasn't gone away yet. But it's SDI, it's got HDMI in it as well, so it can handle things like computer video images as well. And the idea is that this can do some very high-end processing to video signals. To give you an example, the product is called the Fovea F1. It was interesting. I thought I'd ask the gentleman I was working with at Calibre what Fovea stood for, and I went, wait, there's this thing called Google. And it turns out Fovea is the part of the eye where we do our very high-level discrimination of when we're looking at things. It's the center part of our vision. That's the fovea in the back of the eye that captures that and allows us to perceive light and make sense of it. But the Fovea, we entered into a business agreement with them. It's a reseller's agreement, as it's known. It was introduced at IBC. But this type of device is something you would use in live production. 40 of them were used during the World Cup, so this is just a little plug for all the signals in Europe. So it's kind of gone through its inauguration into the broadcast industry, being as a small company didn't really work in that industry. So that's the gadget I brought along tonight. The content, I'm playing through it, and I'll leave it up and running for a little while. I see that my player has stopped because it hit the end of the. So this is some BBC content that we had in our lab. I loaded up on a small Blackmagic design playout, and I'm playing in 50 hertz original material, and it's being converted to 59.94. And thanks to Paul Roser for the use of his 4K. That's the 4K monitor, Paul?
No, that's just.
Oh, that's just the HD. Okay,
Yeah,
that's the
that's
HD monitor it's playing in. So that would be close to native format. It's 1080p monitor. I've got 1080i coming out of it, so it would be doing the interlacing in the monitor. But that's what I brought tonight as a gadget. It does the hardest thing in video, frame rate conversion. Any questions? Sorry?
The hardware.
This is the hardware right here. This 2RU box right here. Actually, there's one device in it that does the motion estimation that comes from a completely different industry, as I understand. There's also FPGA, and there's some pretty heavy-duty processors in there, so there's some real-time software processing going on. So it's a combination of software, FPGA, and an ASIC, specialized ASIC. So it's a very specialized design. Any other questions?
Is it cheap?
Define cheap.
$10,000?
People,
Not that cheap.
oh.
Okay, where's our salesman? There he is. David.
28K.
28K.
Pound sterling, I said.
No.
Canadian dollar.
Canadian dollars.
Oh, okay.
Loonies, 28,000 loonies. 14,000 loonies. Any other questions? Read.
Yeah, usually with standards converters, especially converting from PAL to NTSC like years ago, the biggest downfall was the credit scroll. The credits are coming up the screen. How does it handle that? I don't see any credit scroll on that. It's all nice pictures.
You'll have to place some credits through it to see, but it will take care of it. You're right. Credit scrolls are the most difficult thing to do. It's interesting. I had described to me one of the hardest things for a motion estimated process, and the other two companies that do this, 4A and Snell, there is content that can break any of these high-end processes. But think of a transparent graphic that's scrolling in front of a human face. When you get into cases like that and you're trying to estimate where the characters should be, it could cause something to happen to the face that's in behind this transparent logo. And in cases like that, what you tend to do is exclude that part of the image and drop it into a linear mode, and then in the other part of the image. So in certain cases like that, you might even want to just exclude the motion estimation because it's breaking. What will happen is it'll look a little bit more pleasing to the eye because the image won't be breaking, but there might be some judder or some blur.
Thank you, Randy. Paul Roser, you're up next. So everyone knows Paul is the former chair of the section and been with simply a long time.
Thankfully, flip some switches. So this is actually showing a little bit of evolution. This is a product that has been at SMPTE a couple times. We've shown it before. We've shown it at boot, or discussed it at boot camp. And this is actually it moving forward. This is Region of Interest Scaler from AJA. The product, the box rather that's doing the magic is here. And one of the things I want to actually mention, this is physically the same box we've been showing for probably a year and a half. But as they've moved forward with their development, they've been enabling things that have sort of been lying dormant in it. And so in the past, we've showed it with just a single region of interest, but this had two scalars in it all along. And so they've moved forward finally to the point where the second scalar is working. So it just uses it's the old ADO kind of metaphor, where we're just using any old joystick. This happens to be just a cheapo USB one, things like $100. And we've got the one region of interest there that happens to be going to this monitor. And let me just grab my mouse to flip it over to the controlling the other scalar. And now the red box is moving around. So that's two SDI outputs from a 4K raster. And again, in terms of the evolution, something else that was laying dormant in the product all along that they've gotten running now. It actually works on this as well, but I can't really tip that up where you can see it. So I'll just bring up this interface here, and you actually have control of the color. Not on the individual boxes, but on the full raster. And so, just through this interface, and the clumsy mouse that I'm holding, I've got them ganged right now, but we can manipulate the typical colors kind of controls, gamma, lift, gain, mean, all those sorts of things. Oops, I'm trying to do it on the wrong spot. So just with the sliders here, we can manipulate the color in the entire raster of the image. But a whole lot of math really going on in here. Again, a 4K image that we've got two arbitrary, they call them arbitrary region of interest because they're not a set size. The panel here, stand back so I can read the tiny little labels. but there's presets on it for various sizes, 1080, 720, SD. It's possible to set lockouts in there so you can't go below a certain resolution. It's been used in things like sporting events where that's actually turned off, where they can go in really tight on things. Been used by NFL where a call was actually reversed based on this box and the detail they could get on something. They just happened to catch it. But it's again a bit of a look at the evolution of a product that we've shown before. I don't know if there's any questions about it. It's also much easier. I know tiny little monitors comparatively there. It's something if you want to take a look at it, after that's sort of right, come up to the front and take a look. But that's pretty much it. We've sort of talked about it in the past.
There we go.
Thank you, Paul. I guess our last gadget for the night is another Paul. So we have Paul Briska, who's everyone knows Paul, our current chair. So hand over to Paul now.
Let's see what happens. I'm going to use my outdoor voice. I hope that's okay with everybody. Let's see if this adapter hangs on me here. We've been having some video trouble today. Isn't that nice? So nobody's ever done a demo with a computer before, right? We have no idea what's going on here. So we just have to reboot and then tell it we have a VGA plugged in because Apple forgot what VGA was many, many years ago. So what I'm going to talk about tonight, though, is an interesting little thing. I have a confession to make. I have an alter ego. A few of you who know me already know I'm a radio ham. I was bit at age 12 and got my license at age 13 when I had nothing better to do before I discovered about girls and stuff. And so I've got this thing about playing with radios and radio propagation and radio circuitry and RF, and it's just a thing, and I can't explain myself, and I won't try. However, out of that comes occasionally, oh please, please light. It looks promising, you know, it really does. Why don't they light?
Well, the projector is on.
Yeah, I know it's on, I know it's on. It's not like when I plug in a VGA E-DID. Anyway, so one of the things that interests me and always has is radio reception. And I don't mean listening to radio so much, but the technology used for radio reception. And radio hams are famous for listening to the weakest possible signal way down deep in the noise from the farthest reach of the earth and all this kind of nonsense. And that, in some guys, manifests itself as staying up all night to try and actually communicate with that person. And other people just sort of get off on building equipment that's capable of doing that. And we've, in recent years, had quite the revolution in technology, and particularly in radio receivers. So time was, a high-performance communications receiver was a very, very specialized piece of equipment. Wow, this is really making my day. I'll keep talking while I reboot one more time here. Apologize.
You talk and I'll find it.
Okay, well, so what we need to do is boot it up and then try plugging the VGA in. So receivers traditionally were a lot of very, very specialized electronics. They tend to be frequency specific, so a receiver that covers, for example, the shortwave frequencies of 2 to 30 megahertz, inherently by its design isn't really suitable for receiving something in the hundreds of thousands of megahertz range. Instead, you might use that as an intermediate frequency device with a converter that converts down the higher piece of spectrum. Very advanced techniques have been used for the analog front end to find the lowest possible noise floor, yet the highest possible overload intercept point, and things like this. So far, so good. Did it hang the computer completely? No, it didn't. Good. Oh, there's not a battery. Oh, everybody's going at it here. So, there you go. I was going to say. So as the projector is on, right? Yep. Hang on. Switching sources 1, 0, 10. Oh, press run. Yes, how many SMPTE board members just take to light a screen? And I may not be able to light the screen, which is going to be no fun at all because it worked earlier. Well, anyway, what's gone on is as follows. We've gone from a heavily analog technology base, just like everything really, to finally seeing digital technology receiver, starting at the audio frequency stages, working its way back to the intermediate frequencies, the local oscillators, right into the front end. And so what I want to show you tonight is a new receiver technology and a manifestation of it that is so unbelievably inexpensive, it's nuts. But unfortunately, I can't show my fabulous slideshow thanks to whatever combination of nonsense goes on here. So I may only be able to show you the live demo on my little tiny screen, and you may actually all have to come up and gather around, which is kind of unfortunate. But maybe we'll bear with a second longer here. No?
Manny, you know anything about this?
Yeah, I mean, Manny knows.
That was the wrong one.
I am in awe. I am in awe.
And Paul, you saw this at IBC?
No. This is something I've been playing with now a little bit. This is all my own basement nonsense in whatever little spare time I have. Oh, that's promising. Something.
Hey, it took me.
Manny. All right, the hero of the evening. So, what I want to talk to you about then is the capabilities of this little receiver, and then I actually want to show you this little receiver, and then I want to talk to you about how much money this little receiver costs, because this is just, it's nuts, I think is the way to describe that. So let me, somewhere here, you can hear me without that, can't you?
See if that's the source of the buzz.
Oh, the buzz, okay. If you don't know what the buzz is, all right, it's me.
Humbucking coils?
There we go.
No, it's a ground loop from the projector. When I plug in the audio. We're going to need the audio later. I'll unplug it for now. So, let me just talk about a hypothetical communications receiver for a second. Let's talk about a receiver that can receive from DC to, say, 2 gigahertz. Now, that's a fair span of frequency, and because I said DC, it's an infinite number of octaves, so it's kind of irrelevant. But let's say, something that covers the VLF frequencies in the tens of kilohertz up to, say, 2 gigs. Now, right off the top, that's not a receiver you can particularly buy historically because of the extremely broad spectral coverage. We're also looking for high sensitivity, something on the order of a half a microvolt to produce a reasonably audible signal from an antenna input, something like 113 dBm, 113 dB below a milliwatt of power. That's not, by the way, a very good receiver. That's a nominal receiver, but it's a good starting point. Now, in the receiver, you want to control the bandwidth of the signal you're going to demodulate. You do that with a passband filter normally in the intermediate frequency stage, or as is more modernly called, a roofing filter. So let's say we want a roofing filter that's adjustable in bandwidth from 1 hertz to 250 kilohertz. So 1 hertz or a couple of hundred hertz would accommodate very, very slow speed Morse code signals, for example. 250 kilohertz would accommodate FM stereo broadcast. We want demodulators in this receiver that will receive wideband FM, including decoding of stereo, narrowband FM, good old AM, single sideband, and CW Morse code demodulation. So all the different demodulators you normally would expect in an analog receiver. We want automatic gain control, we want noise reduction, and we want an adjustable squelch. So when you're listening to something that's a noisy background, you can kill the background, just simply clip the background until a signal comes, and then you open the audio gate. Let's also equip this receiver with a spectrum display. Let's say you can look at the screen and you can see a megahertz either side of the center frequency you're listening to on this receiver. That's a pretty cool feature. And let's also give it a programmable FFT bin count, so essentially your resolution, your frequency resolution, and a windowing method that's adjustable. So you've got a configurable spectrum analyzer in this receiver. And let's also give it a waterfall and a real-time spectrum display. Those who don't know what a waterfall is may see it, depending on how well the computer behaves. You may see that in a minute. Let's also provide frequency memories, say an arbitrarily infinite number of frequencies can be stored for quick recall. You just click on CBC FM and it pops up. You click on Jim's Taxi and you're listening to Jim's Taxi service. Audio and baseband spectrum recording. This is really cool, by the way, in a receiver. Audio recording, no big deal. The audio comes out, you record it. Baseband spectrum recording is neat because what I'm talking about doing is recording this 2 megahertz of width to disk in real time. So instead of having to actually tune around and find a signal in real time, you can go back later and play that piece of spectrum for that piece of time. And then you can go and tune and find out what signals were in it. So you actually can record a piece of spectrum with this kind of receiver. And let's finally make it network accessible and internet accessible. So it's a pretty nice receiver description. And so that, for example, is a domestic, non-commercial one you can buy that does a lot of this stuff. It's got a spectrum display, it goes over 1 gigahertz, it's got some web page thingy. I think it's about $5,500 or something. You can spend more money And these are both modern and ancient versions of things that sort of do some of this stuff. I wouldn't want to guess what the Raycals were, the old RA-17, just because it's beautiful. But receivers like this are insanely expensive. They're meant for air traffic control applications. They're super high reliability, 5 nines operation, all this stuff. Not the sort of thing you can afford to play with if you're just a guy like me who's a radio hammer experimenter who wants to play with something. But these meet most of those requirements to varying degrees. So what exactly does this ultimate receiver look like? Well, I digress briefly. For $9.62 Canadian, landed at your door in less than 21 days, you can go on eBay and buy a DVB-T receiver stick. So if you're in Europe, you can order this thing up, plug it in your laptop, run their little CD, and you've got a terrestrial over-the-air TV receiver. Now, it doesn't work in North America because we had to, of course, do ATSC. We could never do anything the way the world does. So we have a difficult, awkward, hard-to-decode ATSC standard for which this stick will not work. And in fact, there is no $9.95 solution for North America, only for Europe. But it's a cute little gizmo and has no use in North America. Until, of course, software hackers come along who are also radio hams and say, geez, you know, there's hardware inside that thing I can mess with. There's what it actually looks like. That's what your 10 bucks gets you, is that. Oh, and you get a little V antenna with it as well, and a remote control you can't use. There's what's inside. Just about nothing. And from a block diagram point of view, here's what's inside. And have a look. It's got a low noise amplifier. It's got a fractional end synthesizer, so you can synthesize a local oscillator frequency of some kind. And it's got an I and a Q mixer. So it's mixing quadrature signals down to some baseband frequency. And then what isn't shown in this block diagram is there are 2 A to D converters here. And the 2 A to D converters stream the IQ samples at the sample rate out onto the USB interface. So if you want to receive DVB-T TV, that's fine. You set up the fractional end PLL for the right time, the right local oscillator frequency. Signal comes in, you get I and Q, you shove them out the USB, and the software takes care of giving you a picture and a sound. And these bright-eyed guys said to themselves, well, we can do that. We can push samples, and we can plug in whatever frequency we want here. Let's set this to 99.1 megahertz. And we're now sampling the center frequency of CBL-FM, stereo, well, not stereo, actually, CBL-FM in Toronto, plus and minus a megahertz worth of samples, depending how fast you sample it, and we send that off to the computer. And we can now run software on the computer to demodulate this stuff. And I am, hopefully, without much to do, able to actually start up and run this thing and show you what it does. Assuming everything works happily, which, who knows. So if you bear with a second, see if the screen goes completely wank on me here. Yeah, there we go. Bad. So let me just get you out of the way a sec. And somewhere here, I lost my folder. So there's quite a number of apps that have been written to drive this little device, and the one I'm going to use here is called GQRX. It's an open source development. And if I'm lucky, it will not give me a warning message and it will run. Well, the spinny wheel is not good. This is not good too, but let's see what happens. Well, some guy's open source project, everybody's contributing to the code tree. Okay, so this actually looks reasonable. We're going to use this little device here called the RTL SDR, and we're going to sample at 1.5 megahertz, so we'll get a 3 megahertz wide window. I'm sorry, no, we'll get a 1.5 megahertz wide window with IQ sample. So we're just going to run this little program, and it should give me a GUI, and I should be able to give you one. Come? So close. Right. So we're talking to this little dongle that's plugged in my computer. There's the little DVB antenna that comes with it. Obviously not a very useful antenna for much. And let's set to 99.1. We're going to do wideband FM stereo. We're going to receive it. Somewhere here will be a volume control for this thing. Oh. Let me just, excuse me a second, let me just get loud, the control moves a lot.
During resuscitation.
I think that there is a lot.
Now, you can see lots of little spikes going on here from other crap in the room generating a whole spectrum full of nonsense, but there you go, right off air, CBL FM, at 99.1. If I wanted to go listen to something different, like the weather forecast, 162.4, I think. And that's narrowband. So one big difference between this and a very expensive receiver is the quality of the time base, and this one happens to be 22 parts per million off frequency. So as soon as I set that up, you should see that work. Oh, there. So there it is on frequency. Wonder what's going on at 800 megs? I don't know how well shielded we are in here. Wow. We're really not seeing much in here tonight. Get a little more gain going. What's this? Some two-way radio thing up here. I can control the center frequency of the spectrum. I can remember how, zoom in on the spectrum. Let's go back to a signal. 162.4, where are you? Here you come. See him coming down there? There he is. 162.402. And if we want to see a little more detail on him, I can go to the FFT and I can just look at him with more bins. And I can filter him up and down. There he is. So this little guy, as he comes out of the box, without modification, will cover somewhere around 40 megahertz up to about 1.7 gigahertz. And the behavior of the software is the same on all frequencies. You essentially dial up your frequency, dial up your demodulator, dial up your filter, and you have a receiver. The amazing part of this thing, in my mind, is the capability of this thing. It just blows my mind that this is even feasible. And the interesting part about it is the number of applications people have written for this thing. So, one of them, there we go. So these are the applications that currently exist for this thing. As a general purpose receiver, you just saw the one little app here. And after the meeting, by the way, you can come up and play with it and have a look. There must be 25 different SDR, software-defined radio apps to run this little stick now. They all have different screen presentations, but they all do basically the same kind of functionality. It's a great little spectrum display. When you bring the IF frequency out of your ham gear, you can then have a look at all the signals around the frequency you're listening to, which is kind of neat. It's a great little lab analyzer. Anybody want to scan a receiver, it's $10. You can listen to anything you want on VHF or UHF communications radios. There are apps written for weather satellite data decoding, picture display, weather balloon tracking, and data display. If you're into aviation, you're familiar with ADS-B, the data service that's used to bring fleet data down from aircrafts, and ACARS, a different version of a similar thing. There are apps for both. The ADS-B one is kind of neat because you get these little messages going by on your screen. You can see all the traffic from the pilot. He's booking his hotel room for his destination and all this stuff. And ACARS is neat because it actually gives the lat and long of the aircraft, and one of the applications actually superimposes it onto Google Earth. So you run the app and you just sit and monitor ACARS, and after a while you see all these planes flying over their flight paths, and sure enough you see one coming for your neighborhood, and you go outside and he goes over when it's supposed to go over. Digital two-way radio, P25, there's software now to decode that. So if you thought you had a secure digital two-way radio system, there are people who have software for the $10 dongle that can hack you. Trunk radio, this is where they have an analog two-way radio system and multiple channels, and then they hop channel to channel so you can't follow the conversation. That's long been hacked, so you can get software to listen to Metro Police, Toronto Fire, all the whatever people may want to listen to on here. This is one of my favorites. Depending on the band, you can do cellular telephone analysis and intercept, so you can actually do various nasty things on the cell bands. Not all the bands, because we only go up to 2 gigs, but certainly on the old 700-800 meg bands. And digital radio mondial doesn't mean a lot for us, but for people who live in the DRM supported area, it's pretty cool. The other thing, I mentioned this covers 40 megs to 2 gigs. There's also a mod, of course, what do guys figure out as soon as they get one of these things, how to take it apart and do a mod. And the mod is to actually allow you coverage from DC to 50 megs. So between the little modded change to the unit and its fundamental operation with the funny little antenna, the thing will cover DC to about 1700 megs, I think, is what they really go to in reality. And so I'll just tell you about my little project, because being a ham, I have a project. It's one of these things that marinates on the workbench. And the project is to use one of these things with a Raspberry Pi. And actually, if nobody's seen a Raspberry Pi, I brought one just to show you. And basically, the Raspberry Pi hosts the client application that talks to the USB stick. And the Raspberry Pi has a Wi-Fi network connection, so you can talk to the Raspberry Pi over the network. And then what it does is it streams its samples onto the network, onto a TCP session that it establishes with the GUI. So the GUI is running on my laptop. The little dongle is actually on the Raspberry Pi somewhere, and I connect to the Raspberry Pi, and it pushes samples back to me just like I would have plugged in my own USB interface. So I send control, such as what frequency I want, I send to the device, and it pours samples back across the network. And then get to it from the internet. So these elements are all actually done and running. I was going to bring the Raspberry Pi to show you tonight, but it's just not finished enough to actually boot up with enough confidence to make it run. But basically, it's a remote internet receiver that'll receive DC to 2 gigs. The fun part comes in what I call phase 2, and I may get to this over the winter. And this is to add to this an active antenna. So a little antenna like this, but a voltage probe, an E-field antenna, but with an impedance converter, an active impedance converter in it to actually allow me to get some signals out of it down at low frequencies right up through VHF, UHF. And then battery and solar. So you put a battery with this thing and you solar charge it. So you've now got this thing available to run on solar with battery and in a weatherproof housing. And so this is my bizarre little project because it's a remote solar powered, self-contained antenna, wireless, internet accessible, all-band receiver. So the idea of a wireless receiver, the whole idea of having the receiver up on the roof with no wires connecting to it, just somehow resonates with my brain. So that's the nature of this project. And I'm hoping to actually, maybe I'll bring that for a little 5-minute show until come the end of the SMPTE season if I get to it over the winter. So that's actually, I just wanted to show you, is how this kind of capability has gone from the Legion, very quickly too, from the Legion, very expensive, very specialized equipment, down to something you can buy for $10 and software you can download off the internet.
Very cool.
And pretty cool little gadget, in my opinion. So that's my gadget. And you're welcome to come down and play with it. Any questions you may have, ask them now, or when we're done, you're welcome to come and play, and I'll show you what I can.
Where did you buy it, Paul?
I don't know, I went on eBay and so the search term, actually, I had an ad here. Where was it? Here, yeah. So this is one. RTL-SDR is a good link. And basically, well, if you shoot me a note, I can tell you a few things to look for, but just Google around, you'll find these things. This is the latest little, it's just super small, which is why I picked this one. Just insanely small. Now there are limitations, by the way. The time-based oscillator in this thing is cheap. It's a 10-cent crystal. So when you're up at hundreds of megahertz, your ability to actually have a nice, stable, and accurate reference to dial-in frequency is poor. So that's one thing that needs improvement here. The other thing is, you can imagine, if we're hearing down at minus 115 or minus 120 dBm, the noise profile inside this platform is going to be very tough to achieve, right? So additional shielding, additional techniques to get the noise decoupled from the front-end part of it is required. So it's by no means equivalent to a $20,000 or $30,000 communications receiver. That said, it does most of what one of those does, and for casual use, it's entirely acceptable. So, it's cheap and dirty, but it just blows me away that something that wasn't even intended for the application was picked up by a bunch of hobbyists, most of them not radio hams, they're just computer geeky guys who know a bit about radio. And the next thing you know, this thing is exploited up the yin-yang for all manner of stuff. It's very, very cool.
What kind of antenna interface is that?
So this has the hideous, I think it's called an MCX connector. It's the funny push-on European mini coax thing. Anybody know about MCX? I think this is called an MCX. Is that what it's called? Anybody know? Huh?
I think so.
Yeah, it's a horrible, horrible little connector. Just the worst. So actually this is just stock out of the box with the little factory with the antenna. And I normally would run this on USB extension, which I brought, but nobody has a need for it. But what you do is you modify them to either put an SMA connector on it,
or hang a piece of coax out with a BNC female on the end so it's a little more usable. But yeah, that's what it comes with. Because again, they expect you to be in a hotel somewhere, you know, watching off-air TV, trying to find a signal with a little antenna. And it was only ever intended for receiving those bands anyway by the original designer. So that's it. You make your question, or you just, no, you just wait. So with that, thank you all for attending, and appreciate you coming. Look forward to seeing you all next month, and if you'd like to come up and see any of the gear or talk with any of the people that presented it, by all means, now's the time. Thank you all, see you next month.